Hello, my name is Dejan Grubisic, and today I'm going to present our paper, Priority Sampling of Large Language Models for Compilers. The first question is, how does compiler work? In this example, we start from an example written in C. We are giving the file to the machine called compiler, which also takes a list of optimization sequences that needs to be applied on a given code and outputs executable format. In today's presentation, we are going to see how can we predict the optimal path list for a given input code. But first, we need to ask ourselves, what is a good representation of a code? Traditionally, machine learning approaches for compiler would use a list of feature vectors to represent code, or to represent code with some kind of graph that in which contains a feature vector in each node. But this kind of representation always have some loss of information, and they are task specific. Alternative to this is to use text. The only problem with text is until recently we didn't have machine learning architecture to handle text and to map it to the good optimization sequence. With LLMs, we are able to do that. In their paper, Cummins et al. Proposed the following approach. They constructed a prompt giving it input code written as LLVM IR assembly code, and they're trying to map it in their training phase to produce a list of optimization sequence which perfectly optimize this code, together with instruction counts of starting code and optimized code, and at the end, the model is asked to write the optimized code itself. This approach enables us to use inference phase and to generate only optimization passes, which are further going to be sent to compiler, which is going to produce optimized code. This way, we are saving the semantics of the code and using LLM to just produce optimization strategy. When it comes to comparison with alternatives, this approach doesn't use any search, and therefore it has zero compilation, while alternatives has hundreds of thousands and even million compilations to achieve their performance. When it comes to the performance, which is the code size in our case, we can see here that autotuner used for training set achieves 5.03% improvement over default -OZ optimization, while two state-of-the-art approach, autophase and Corset MVP, have regressions. And finally, our approach achieves 3.03% improvement over default optimizations. And even though this approach has better performance than alternatives, there is still a gap between autotuner and the given approach. In this presentation, we are asking, can we do better than this? Can we bridge the gap between autotuner and the LLM? And the answer is yes, we can. So we are going to focus on the next generation of LLM. Here, we are starting for some input tokens. We are sending this sequence to large language models. And for each token, it is producing a probability distribution for each token that can be selected next. Usually, people just use argmax as a best next token and go with that. In addition to this, we can use also a softmax function and temperature sampling to sample this distribution and therefore produce multiple different answers. When it comes to temperature in the name, temperature is added constant here that can make this distribution sharper if the temperature is less than 1. And this caused us to focus our choices only to few places that have high probabilities. Or we can make the distribution flatter if the temperature is higher than 1. And some people call this being more creative when it comes to language models. Sampling the model this way, we are able to produce multiple sequences that can outperform the starting sequence of optimization flag that model provides. We can see this in our results as well. We evaluated this approach on 50,000 test examples, And each color here represents different number of samples that we use for each examples. If we use one sample, which is a blue line, and we increase temperature on x-axis, we can see that performance drops with increase of temperature. But as soon as we use multiple samples, we can see that performance actually increases up to the point and then drops if the temperature is too high. With 100 samples, we are able to reach 4.86% over minus OZ, which is about 98% of the autotuner's improvement, which comes really close to our test set. The problem with this approach is that temperature sampling creates a lot of duplicates and illegal sequences. You get duplicates when you're sampling probability distribution because it is high chance that you're going to select some tokens again and again, especially if the sequence is short. When it comes to illegal sequences, with increase of temperature, you can select the next tokens that are not coherent and doesn't apply to semantics that we expect, especially in producing LLVM optimization sequences. On this chart, we are showing number of unique samples that we can get given the number of samples that we tried. And with temperature sampling that we used here, and to be more specific, we used Nucleus Sampling, we get less than 5 unique samples for 100 tried examples. While with priority samplings that we are about to describe in this paper, we are forcing each sample to be unique, therefore generating 100 diverse samples. So let's see the priority sampling algorithm. On this, we are presenting each node as a token, and above each node, we write the next token probabilities sorted from above to down. And underneath the token, we are writing the token prefix, which is a sequence of tokens that comes before the given token. When we expand the next token, we are expanding only the token with the highest probability, while we are putting all alternatives to priority queue. It is important to say here that we constrain alternatives with the regular expression matching to keep only the sequences that adhere to the grammar that we set, which is LLVM IR grammar defined by opt command. Continuing this, we are expanding each next token by expanding the best token and putting all alternatives to priority queue. Eventually, we are going to generate the whole sample, which results in run passes minus loop simplify here, which are all the first tokens that we can expand. And the next question is, what is going to be the next token? And the answer here is that we are just taking from priority queue the prefix, which is going to have the highest probability given the previous tokens. And in this case, this is the prefix run passes minus loop un. When we expand this, we are getting the new sample, which is run passes loop unroll. And again, we are expanding the next samples in the same fashion. And we are getting the final sample, which is run passes minus OZ minus SCCP. And therefore, we can guarantee that each of these samples are going to be unique. We are showing on this graph the results of priority sampling. Here, we are on x-axis showing the number of samples we are trying and cumulative performance on y-axis. First, we are showing with a brown random sampling, which is just trying different optimization sequences sample number of times. Next, we can see the greedy decoding, which is taking the argmax of our language model. After that, we get nucleus sampling, which is using a different temperature to create different samples and take the best performance out of all of these samples. And finally, we see the performance of priority sampling. Priority sampling produces about 91% of autotuner improvement over minus OZ in just 5 samples. With 30 samples, you're matching the performance of the autotuner used for training set. And with 100 samples, you're even getting 100.2% of the autotuner used for training set. This is a surprising result because we didn't train our model to outperform the training data, but we did it by using sampling and trying different alternatives. We also used a few ablations here. We ablate on using and not using regular expressions, constraining a branching factor of this augmented tree that we are expanding, and also using a geometric mean of probabilities of token prefix for priority queue. From this, we can see that performance doesn't differ much for all of these ablations, and that we are reaching similar amount of performance, similar to just straight priority sampling. With this, I would like to finish and once again to repeat what are the takeaways. So the first one is that large language model could predict LLVM optimization flags pretty successfully, originally getting about 3% improvement over default -OZ optimization without any compilations. Next, with temperature sampling, we are getting about 98% performance of autotuner with 100 samples, but this creates duplicates and illegal sequences. With priority samplings, we create no duplicates or illegal sequences because we use regular expression to expand only sequences that are legal according to our grammar, and we have no duplicates because we expand only one time from priority queue, making sure that each next token is going to be expanded with a different continuation. And finally, with 5 samples, we are achieving about 91% of autotuners performance, while with more than 30 samples, we are outperforming autotuner used for training generation. With this, I would like to finish and invite you to read our papers in full. Thank you so much.